want to say welcome to everyone to the topics in surgical informatics, which is our regular journal club here at the Surgical Informatics Lab. And today we'll be discussing a very interesting paper that was recently published in Nature Scientific Reports, which is a randomized controlled trial comparing real-time AI instruction versus human instruction for teaching surgical skills. And we're excited to have the lead author of the study with us, Dr. Recai Yilmaz, here joining us for our discussion of this paper. So Recai, welcome, and Guillaume, I'll pass it back off to you so that you can introduce the study.
Sounds good. All right. Just move these things around. Okay. So is everyone seeing the slides in presenter mode right now? Okay, great. Like Jayson mentioned, we're going to be discussing this paper, Real-Time Multifaceted Artificial Intelligence versus In-Person Instruction in Teaching Surgical Technical Skills, which was a randomized controlled trial published in Nature Scientific Reports. And we have the pleasure of having the first author of this paper here with us today. So just a very brief background. We'll be talking in this paper about this intelligent continuous expertise monitoring system, which was developed at McGill, which was integrated into a neurosurgery kind of VR simulator, which is a VR platform for performing brain tumor resections. And what this system is a neural network that is able to assess surgical bimanual performance at 0.2-second intervals during these simulations. So this was trained on 156 virtually simulated tumor resection tasks. It's a LSTM-based neural network. And what it's capable of doing is providing coaching and risk assessments for critical metrics during the simulation to participants in the simulation. And then when it was initially published, was also able to give some post-task AI feedback on participants' performance. And what this paper we'll be talking about today is kind of taking the next step and going from post-task AI feedback to real-time AI feedback, and one, what that might look like, but also how that would compare to expert real-time feedback on a simulated task. And so in this study, there were 99 total participants that were split into 3 different groups that were all going to be performing the same set of simulations. So the tasks in this case were a simulated neurosurgery task, followed then at the end by a realistic brain tumor resection task. And in each group, all the participants had kind of 5 repetitions of the practice task with or without real-time feedback. And then finally, with a final performance on this realistic brain tumor resection task that they all saw for the first time. So in the first group, the post-hoc instruction group, participants only received post-hoc benchmark feedback that is essentially the metrics of their performance on this task at the end of each simulation, so they could kind of see how they were doing. In the second group, the real-time artificial intelligence instruction, as participants performed the simulated tasks, they received real-time AI auditory feedback on how they were performing based on the metrics that's collected by the ISEMS system, which we'll get into a little more detail in the next slide. And then finally, in the in-person expert instruction group, very similar to the real-time AI instruction group, participants received in-person instruction from senior neurosurgery residents during the task based on their performance. And then at the end, for each of these groups, they all attempted once the realistic brain tumor resection task. So this is kind of a brief overview of how the AI system, AI feedback was given in real time. So as subjects are performing the ongoing operative simulation, real-time data is collected and fed into the AI assessment that is then based on how participants are performing is able to calculate a target score performance as well as measure the different metrics which are shown in that table on the right, and then is able to determine whether to provide real-time instruction based on those metrics, and specifically looking at if for at least 1 second participants are deviating from those metrics from an expert threshold by at least one standard deviation. And based on whichever metric the participants are deviating from, the AI will pick a piece of auditory feedback to feedback to the participants. So that was the real-time instruction. And then at the end of the simulation, there's also post-operative feedback, which is clips of video where training performance was one standard deviation below expert level target scores for at least 6 seconds straight. And in that case, the system was able to clip the 10-second clip where this was occurring for that participant to highlight their error, but then also show an expert level demonstration of how to correctly perform the part of the procedure that they had been struggling with. And then just a brief overview of the groups. So these were all medical students with, in general, fairly limited surgical experience. And each of the groups fairly kind of balanced in what year and background they had. So kind of jumping into the results. So the top figure, figure A, shows the composite score. So iCEMS provides a composite score on a scale of -1 to 1, where -1 is a novice and a 1 is an expert. And what we're seeing on the x-axis is the simulated trial overall score. And what we can see in general is that participants generally are getting better over time, which is not surprising, but that participants who are receiving real-time AI instruction appear to be significantly improving, particularly starting at the third and fourth trials, compared not only to the post hoc feedback, but also to the expert instruction. And then further breaking down the overall performance, one interesting finding was when looking at metrics for bleeding risk and injury risk, what the group found was that participants in the real-time AI instruction had significantly less bleeding risk, especially after the third and fourth repetition, and risk of injury in the simulation, even compared to those receiving expert instruction. And again, for coaching, we see similar results where participants in the AI feedback group, outperform the post hoc and perform similarly or sometimes even better than the expert instruction group. Finally, we had talked about there was a scoring on a realistic simulation that each participant attempted once, and we see that the iCEMS composite score during that simulation for both real-time AI instruction and expert instruction is better than post hoc feedback. However, they likely weren't statistically powered in order to find a significant difference in these two. In the scores between these groups. And they also looked at the cognitive load that comes with the different types of feedback that participants are receiving, specifically noting a statistical significant difference in extraneous load when from participants receiving real-time AI instruction which they highlight, there's kind of more to keep track of when you're getting this real-time AI instruction than perhaps with expert instruction as a participant. And then finally, on the the realistic simulation scenario, these were graded by experts using OSATs that were blinded to the rest of the study. And we find that when compared to post hoc feedback for the different OSATs categories, there are statistically significant improvements in the skill rating. And particularly of interest is the hemostasis column, where the real-time AI instruction not only performed post hoc feedback, but also expert instruction, which was a consistent finding compared to the fact that AI instruction seemed to help participants have minimize the bleeding risk during the simulation, whereas with expert instruction, that risk seemed to increase, which was an interesting finding from the paper. So that's kind of going through all the figures that I had. I think now would be a good time to kind of move into a discussion. We had prepared some, questions for Recai, but I don't know if potentially we might just, if you have some comments about the work before we jump into some of the questions that we had prepared.
Well, thanks so much. It was a very great summary of the work. I have some slides regarding the development of the system. I guess that would bring some more context into it. And I have some videos as well. So it would be interesting maybe to see. I'm gonna share my screen. I'm going to share my entire screen just to make sure that it works. My presentation. Okay. So this was the initial paper that we developed this system and kind of validated it using neurosurgery residence data. And these are the simulations that we have used in different works in different papers, and this was the same one. So they did this task 5 times and this one once. And so for the development of this system, we've used only neurosurgeons and medical students data. As you mentioned, there were, I think, 170 something tasks. And then we decided to test this algorithm on senior and junior neurosurgery trainee performance, which is kind of a real-life validation. So in AI, you always do training, validation, and testing. It's just the engineering part. This has to be done. But then in medicine, you also have some real-life validation. For us, it's to measure whether our algorithm is able to track neurosurgical trainees' learning curve as they go from the first year of training to the last year of training. And the algorithm was able to differentiate all 4 groups. Although it was only trained on neurosurgeons and medical students, it was also able to say that a senior resident would be significantly lower in terms of their expertise level than neurosurgeons, and junior residents will be significantly higher than medical students, for example. And then we were also able to see a linear, not exactly linear always, but there was a significant increase from the first year to the last year of training when we looked at the neurosurgical trainee performance. So this was an interesting finding because expertise is something very abstract, if you will. It's yes, a neurosurgeon is an expert, but what defines expertise, we don't know. We cannot quantify it. But through these algorithms, actually, we were able to quantify it, and then we were also able to see if somebody is learning, for example. And I put this video. I think this is one of the interesting videos. So this is a real-time algorithm, and this is a neurosurgeon's performance. And for example, blue means it's a neurosurgeon level, close to 1. But even if this is mostly blue, there are times where the algorithm is saying that this is kind of not an optimal performance. For example, at this moment, this neurosurgeon is not using his bipolar, and that he's getting low scores, and then that actually is going to cause a problem. So at this moment, this algorithm could throw a warning and tell that, hey, this is not optimal, and maybe help a surgeon to avoid this injury. And then we had the algorithm and we saw that it was working, and then we came up with this idea to this is the simulation, by the way. We came up with this idea to add auditory feedback whenever something is too low or too high. The system is telling students to correct it. And that's how we came up with this study that you introduced. Yeah, this is all on my part. If you have any questions.
Great presentation. Thank you even for showing some of those videos. I'm going to let Guillaume and Jayson start with some questions. I have so many, um, uh, but I'll definitely let them kind of get started. But I do want to ask, kind of just to finalize the discussion of the actual paper, what is what are you planning on doing next? So we talked, you showed some of the work of integrating it. You showed that there's this RCT, this randomization that you did to evaluate the different types of tools. What are you where do you want to take this work kind of going forward before we start asking you about some of the details specifically of this analysis?
Yeah, I think there are two ways forward, and we're kind of advancing in both ways. One is in training, so we are kind of trying to find the best way of using the system, whether with an expert or just using AI, and also doing longitudinal studies, because maybe some people needed more time. As you can see, we didn't have significant differences on all the results. Maybe that's people needed more time. There's so much to learn. So we looked at it and we had some results on those as well, like with a longitudinal study. And the other arm would be to apply the same thing in real operations. So right now we are working on obviously in simulation you have the control on everything, and you can record all, because everything is digital. You can track all tissues, bleeding, tumor section, but that doesn't happen in real life. So right now our focus is mostly on trying to get the same data from real operations.
Great.
Yeah, that's fascinating. Actually, that kind of leads into one of the questions I had, which, by the way, I just also want to take a step back and say this is really fascinating work. And I'm actually particularly amazed by the fact that the model trained on the opposite end of the expertise continuum from med student and expert and attending neurosurgeon was then able to stratify out skill levels of different residents, which I think is fascinating. And I'm sure there's something to be learned there about how expertise can be sort of more concretely measured. But to your point about the next step being application of these kinds of real-time feedback tools in real life in the operating room, one of the topics that our lab is very interested in studying is how physicians and algorithms interact with one another, and how they interact in particular when they sort of don't agree with when their sort of recommendations sort of don't agree with one another. And so the real world is obviously much messier than these sort of controlled neat experiments are. And so how do you envision sort of trainees and faculty and these types of algorithms all collaborating with one another in the operating room in particular? How do you envision human expert real-time feedback collaborating with AI real-time feedback in the real world?
Yeah, that's something we were like thinking about, but yeah. So I guess like experts are always experts. So like I guess the best scenario would be having expert to supervise an AI model. And if there's a disagreement, I guess AI models should fit and learn like how the expert handles the situation. Because OR is not a like it's not an environment for like trial and error. And that's why one approach we had was to like have experts watch a video and rate the video like OSATs, but this time just to train an AI model. So if that's a good procedure, the expert is telling that, hey, this is a good procedure done, like perfectly done. So it should be treated that way by AI. And there are, of course, like other examples that would receive lower scores. So I think that that's the way for future probably. And on the safe to be on the safe side, like you use the expertise of the surgeon and train the model that can function like in other operative rooms that may not have the same type of expertise. Yeah. Does it answer all the question or I
Yeah, that does
guess.
actually. I think
Mhm.
the idea of training a model based on um, a human expert giving feedback or giving real time feedback to a trainee is, I think, is a very interesting direction.
Mhm.
Yeah, I can ask one of the questions I had thought of too reading this was, I think something to think about, and I don't know if your group has thought about it, is what are your thoughts about what types of students or where students are in their training path might benefit kind of the most from AI-driven feedback? Do you think these types of systems are maybe better suited for like medical students, interns that could really, gain a lot from just kind of any general instruction at the beginning of their training, versus when you're then thinking about maybe like a senior resident or a fellow, that's when they really benefit from the in-person expert instruction. Have you kind of thought about who these types of systems might help out more? And, should we invest maybe in AI systems for early training and kind of leave the later instruction for experts, or yeah, kind of that dynamic?
Yeah, I think like there's a room for all applications. The reason why we chose medical students and try to train them to a neurosurgeon level because of there is this huge difference. If there's huge difference, you're more likely to like make something significant like in their learning. But as you go to upper levels, the knowledge gap will decrease, and like it's gonna take more time and like more, I don't know, detailed instructions to achieve some significant results. I think, of course, the idea would be like maybe prioritizing the situations where there is very high risk, so that you want to like do something using AI. But in our demonstration, I think it was like our models right now is able to teach a medical student, but I don't think that would be very efficient in teaching senior residents because of like they already know so much, and indeed like we also use them as an instructor as well. Yeah.
One very quick question is it follow up to that is one of the things that kind of speaks to what Jayson and Guillaume were mentioning is um, you can imagine that it would be instructive to understand when these pieces of auditory information were and were not followed, and how that actually affected the performance of even the medical student. Do you have data on that specific granularity? In other words, when people change their behavior based on an auditory indication of some sort?
Yeah, one of the studies like I think it's not ready right now, but it's exploring the response. Like some students is able like they do respond, but there are some doesn't respond, and like I think we identified kind of three groups. one responders, one over responders, and one non-responders. But the reason why they're different could be different. Like we were in
Of course.
Montreal, and yeah, some students were like francophones. They spoke French, and like they were speaking English, but they were not as good. That might be one reason, or like some may not be that interested in learning because like it was, these are medical students, and everyone's like interest is different. Sometimes it's just their interest in the study and not in surgery. Yeah, but since we are able to quantify performance, now we are able to identify these three groups and maybe understand why they are there, and like whether we can help, and also learn how quickly they can learn. Yeah.
Why don't we, so this has been fascinating. Why don't we open this up to the rest of the group if there are any other questions that people have for Recai?
I have a question. So first, I want to congratulate Dr. Recai for your work. It's really fascinating and inspiring. Can you show me that video with the with the performance score over time again? I have a question
Yeah.
about that.
Yeah,
With the red dot and blue dot. So as far as I know, the um the degree of expertise is
so it would be
you
this
had
one, right?
yeah. So as far as I know, the degree of the expertise is uh and the the consecutive performance metrics and data, and it's trained by LSTM based model. Is that correct?
Yes.
So since it's a LSTM model, my question is, how do you get these dots over?
It's an LSTM model. So like in AI, we have different ways to train a model. So I guess I can like explain two of them. Like there is one to like it's called many to one prediction. So like you have multiple data points, but you make only one prediction for the entire procedure. And there's another one called many to many prediction. So you have multiple data points and you make multiple like predictions. So because we wanted to see the differences in real time, we did the predictions to many data points. That's why like I have a red point here. Like this decision is made by the same algorithm as this point here. So it knows when you progress from an expert level
But
to like a more novice level.
but the degree of expertise is trained by the data of the whole length of the video originally, right?
Yeah, whole length of the video and putting all the videos together, all the data
And
together.
and how do you predict the the performance score with only like first 5 seconds of the video?
Yeah, like even if you have 2 seconds of performance, you can make predictions because this algorithm like is able to there's no time constraint and it doesn't have to be a certain length for this to be like for this to make predictions. But I think it also this algorithm also considers the sequence in time. So like
Yeah.
I think the longer the procedure is, like longer than 5 seconds, for example, is better because it's gonna understand the context and the movements so that it can make better predictions. But if you just so like I guess I should also say this prediction here is made by also considering the points nearby. Like it's not really an isolated decision. The algorithm also knows what was happening to that point.
So that
So
point represents the time like before and like a period before and after, or is that the period from the beginning to that point?
it's from the beginning to that point, but there is an attention span. Like it doesn't really, the point here doesn't affect that much the decision on here, but the decision next to this point is very important in this decision. You see, like if it's a neighboring point, then that's more important. If something happened a minute ago, it may not be that decisive.
This is really impressive. So is this model developed by you, or is it a open resource?
This model is developed by me and the team. The simulation was obviously there, and we did not put this model out yet, but I guess it can be done in the future.
Yeah, because in our project we are trying to figure out the error segment during the video. So this is quite this matches our scope. So I'm really interested in how you make this. So this is very impressive.
Yeah, I think I put the codes with the first papers, and if you want to check the codes, and I think that would explain what I'm saying better, maybe more technical.
That'd be great. So is it
Yeah.
the code is in the paper in digital medicine?
Yes, it's on
Okay, I
GitHub.
read that. I also
Mhm.
read that paper is really good. Thank you.
Okay, sounds good.
So this is excellent. Great discussion. I think that these discussions always benefit when you have when you have people with a varied expertise, and you can tell that folks have a lot of interest and expertise in this space, and it's really nice to discuss this with someone like yourself who clearly has a substantial expertise here. So we thank you so much for taking the time to discuss this paper, and we hope that maybe in the future you'll join us for a future journal club with us.
Thank you so much.
Thanks so much.